Welcome to Lesson 3, Systems of Linear Equations. And what we're going to do in this lesson is basically look at solving 2 or 3 linear equations at the same time. And that's what's called a system. So you can see, I have a definition here. A system of equations is a group of 2 or possibly more equations containing 2 or more variables. We'll have x and y in 2 equations, and then x, y, and z when there are 3 equations. And these equations are considered simultaneously. In other words, what we're looking at is both equations at the same time. So this is an example here of a system of 2 linear equations. You can see that both of these are linear equations. So a solution to this system would be an ordered pair, an x and a y that go together. And that xy would have to be a solution to both equations. So it would work in the first one and the second one. And so that's where we're usually using systems of equations. You're going to use these a lot, especially in Calc 2. We're using them when we have certain constraints that we have to have on the variables and there's more than one. So we know that both of these situations would have to be true. And then we're looking for what are the x's and y's or a's and b's, whatever the variables might be, that will be true in both cases. So before we talk about how to actually solve them algebraically, I want to just give you a little bit of an overview of the possible scenarios that you would see for systems of 2 linear equations. What is actually happening when you solve it? So we get a little conceptual background to what we're doing. It's always a good idea if you can make sense of what you're learning as opposed to just trying to memorize procedures with no meaning. It's a lot harder to memorize things when they don't mean anything to you. So I will kind of always be trying to get you to think about why things are true or why things are done the way that they are. So let's talk about a system of 2 linear equations. If they're both linear equations in x and y, that means when you graph them, they'll be lines. So if you were to graph both of the equations, then you would have 2 lines on the same set of axes. And in that situation, similar to this picture here, if you graphed both the lines and they share a point of intersection, then that means that that's the solution to the system because that point works on the first line and the second line, right? So what you're really doing is you're finding the point of intersection when you're trying to solve a system of 2 linear equations. And there are 3 different possibilities of what could happen if you were to graph 2 lines. The first one is this picture that we have here. The 2 lines intersect at this one point. And so you have one ordered pair solution, right? One ordered pair solution. So just for lingo, you don't have to memorize this, but just so you're aware of what it means, that if you have a system that does this and there's one solution, that is called a consistent system, or sometimes it's called an independent system. I hear consistent more consistently. Sorry, bad math pun. All right, looking at the next page. The second option, if you're graphing 2 lines, is you can graph them and they'll never intersect because they're parallel. So if you graph them and they have the same slope as we learned in the last lesson, and they are parallel, then this system will have no solution, okay? And those are called inconsistent systems. So if you were to graph this and you were asked for a solution, your solution would be none. And then last but not least, the third option is that they're the same line. So if it intersects at more than one point, like 2 points, there's only one way to draw that line. And so basically both equations would be the same line and it would be graphed right on top of itself, essentially. So then you have an infinite number of solutions. Every single point on that line is a solution. So not every point in the world, like this point over here and this point over here, those aren't solutions, but all of the points actually on this line are. And so the vocab word we use to describe that would be dependent. Okay. In general, I'm not going to have you solve systems of equations by graphing them. Can you think about why that might be somewhat inefficient? I mean, it's great in the first example here. Oh, No, it's not great. In fact, let me zoom in on that just a little bit more. What a great example. If you didn't have this coordinate pair written right there, how in the name of goodness would you try to figure out what the x and the y coordinate of that point is? You wouldn't. You wouldn't get it right. You would not guess 7/5 over negative 11/5. So solving a system by graphing the two lines is usually only very productive if your solution lands right on a corner, whole number x and y. But fractions are very often part of our solutions. So in general, I don't really expect or even think it's a great idea to solve by graphing as the method you're going to use, but it is a great way to understand what is happening when you solve algebraically. So we are going to talk about the two different ways